Welcome back to Physics 141 Online. The next topic in our discussion of mechanics is a special kind of motion called uniform circular motion. And what we want to do is think about a particle or an object with mass m moving with constant speed in a circular path that has a radius r. And we can figure out a very special expression for the acceleration that this object has by using some very simple vector algebra. So let's use a simple vector diagram to calculate this average acceleration, and we'll look at an initial point and a final point. And it should be pretty clear that for an object undergoing circular motion, as shown here in the yellow circle, that at any given point its instantaneous velocity is tangent to the circle. So at the initial point we can see the arrow indicated by v sub I. That's its initial velocity direction. And then at a short time later, as it's going clockwise around the circle, it's at a final point, and v final is going to be the direction of its velocity vector. And we're saying that the object is moving with a constant speed, so although these two vectors have different directions, their magnitudes are the same. Now, we can label a little triangle that has one point at the center of the circle and then goes to those initial and final points, and see that there's a triangle that has an angle we can label delta theta, and delta s is the side of the triangle opposite that angle, and that's the distance traveled from the initial point to the final point by this object. Now we can make a vector diagram showing the change in the velocity over this short time interval. And remember that delta v always represents final minus initial. So delta v will be v final minus v initial. Now v final is indicated here, and so I've picked that vector up and moved it over here into the right hand side, and that's v final. And when we subtract a vector, we add the opposite of it. So we take v initial, we flip it over in the opposite direction, and then move it over here and put its tail at the head of v final. So what I've constructed is v final plus the negative of v initial. And delta v is the vector that results. It's the difference in those two final and initial vectors. So it's pretty easy to see, since v final and v initial have the same magnitude, that by comparison to the triangle on the left hand side, those two triangles are similar to each other, because the angle delta theta is the same for both, and the two sides are the same in magnitude. And so as a result, there's going to be a simple proportionality relationship that we can write down for similar triangles. And we know that, of course, v final and v initial have the same magnitude. We'll just call it v, in the same way that the two sides of the triangle on the left-hand side have r as their magnitudes. So we can make the relationship that shows that delta s, the side opposite the angle delta theta, divided by delta v, delta s divided by delta v would be the same as r divided by v. Or we can say that delta s divided by r is the same as delta v divided by v. And that's just one of the ratios that holds true for similar triangles. What's nice about that relationship is it's going to allow us to write down an expression for the acceleration of this object. So here is the proportionality that we just worked out based on the similar triangles. And now we can solve for delta v from that, just multiplying both sides by v. So we get that delta v is v delta s over r. Now the acceleration, the average acceleration between those 2 points, is delta v divided by delta t. So we just take both sides of the equation in the middle, divide them by delta t, and we see what we find over here is v delta s over r delta t. Now delta s over delta t, that's the displacement divided by the time. And so that is the average velocity, or just v. So in the limit where delta t goes to 0, that average velocity, or sorry, that average acceleration, the average velocity becomes the instantaneous velocity. And so the delta v over delta t, which really represents the average acceleration, when we take the limit as delta t goes to 0, it becomes the instantaneous acceleration. And so we end up with v over r times this limit, which I've already argued is the same as the instantaneous velocity. So we just get that the acceleration in the centripetal direction, or in the radial direction, is v squared over r. Centripetal means center-seeking, or pointing towards the center. And as we saw, I'll flip back just a couple of slides here, as we saw, that vector points toward the center of the circle. No matter where the object is on the circular path, it's always undergoing an acceleration directed towards the center of the circle. Now, that might seem strange that it's accelerating, even though its speed isn't changing. But remember, acceleration is the change in velocity, and velocity is a vector. So even if the speed isn't changing, if the direction of the velocity is changing, then that means there must be acceleration going on. So this formula for the acceleration of an object that's undergoing uniform circular motion is very special, and it gives us another tool that we can use to analyze the motion of objects that are undergoing circular motion. So what I'd like to do is describe an example problem and then go ahead and solve it. It's similar to some of the homework problems that you will find in this section. It says that there's a car of mass m that's driving over a hill of height h whose shape near the top can be approximated by a circular arc. This is what we often do. Even though an object may not undergo circular motion completely around the circle, if part of its motion can be approximated as a circular path, then we can use this special formula for the acceleration. The question then is, how fast can the car be moving and stay in contact with the road at the top of the hill? You might have some intuition that would say that if the car is going up over this hill too fast, it may actually fly off the road surface at the top. So what we want to know is, how fast can it travel at the top and still remain in contact with the road? And now I'll switch over to my notepad so that I can show you the solution to this problem. Okay, let's look at this problem, and I will redraw the sketch that you saw just a minute ago on my slide. It's a little bit hard to redraw it carefully, but it doesn't have to be perfect. It just has to be understandable. So here is the approximate path that this object is taking, and what we're going to do is assume that this hill can at least approximately be regarded as part of a circle. So that here is the circle, and it said that the hill has a height h, right? So the way that the sketch was drawn, it was clear that that height is the same as the radius of this circular path. So at the very top of the hill, this car is moving, and right at the very top, of course, its speed, v, would be the velocity vector would be directed horizontally, and we want to work out some kind of relationship to find out what the maximum safe velocity is. How fast can the car be moving and stay in contact with the road? All right, that's the question. And so we're really in identifying what kind of a problem this is. It's clearly a Newton's second law problem, but it's for circular motion because of the way the problem was stated. And what that means is we will be able to use our equation for the centripetal or the radial acceleration as v squared over r. And we'll get to that point in just a minute, but it's important to realize at the outset that that's going to be one of the tools that we will use. And what we're looking for then, we're trying to find the v max that will keep the object, the car in this case, in contact with the road. We don't want it to go flying off. Now what about developing a solution? Well, first we're going to draw a free body diagram, and I will draw it over here because it's closer to where the sketch actually is. Here's the car at the very top of the circle, and so you have to ask yourself what forces are acting on it when it's at the very top. And if the car has a mass m, right, then the weight mg is directed downward. That's the earth pulling down on it. And at the very top, of course, the road is pushing up on the car, and that's the normal force of the road on the car's tires. And when it's at the very top of the hill, then that normal force is directed straight upward. I will choose a coordinate system where the y direction will be directed upward, and so we can go ahead based on that and write down Newton's second law. Now wait, you might be asking, aren't there other forces? What about the direction of the velocity? Well, there's no force acting in that direction, and so the car is not accelerating. The car is moving at a constant speed, so there's no net force in that direction at all. So we can proceed to write down the sum of the forces in the y direction. And of course, at the top of the hill, that y direction is also the direction along a line that goes through the center of the circle. And so we'll be able to use this radial acceleration expression in just a minute. So ma sub y is on the right-hand side of the equation. So, keeping with my sign convention, I see that the left-hand side should be n, the normal force, minus mg, the weight, equals the mass times this y component of acceleration. Well, what we've just learned about circular motion tells us that that acceleration has the form v squared over r. Only now, remember, that's directed towards the center of the circle. So at the very top of the hill, the acceleration vector is downward toward the center, which is in the negative y direction. So I'm going to put in here minus v squared over the radius, which I know is the height of the hill. That minus sign is important, and I could have chosen my coordinate direction differently. I could have chosen the y direction to be positive downward. All that would have done is it would have flipped the terms on the left-hand side. So the left-hand side would have been mg minus n, and then the right-hand side would not have had a minus sign. And I'd still get the same equation. So you can do it either way. I've just chosen to do it in this very straightforward manner. So now we see that there's a relationship between the normal force and between the velocity. And let me just solve for the normal force. Solve for n here. I'm going to add mg to both sides. So n equals mg minus mv squared over h. And something interesting about this, it shows that as the car's velocity at the top increases, the normal force decreases. And that's very important. That observation helps us understand what the problem's really asking, because the physics now shows us that the faster you go at the top, the less normal force there will be. And at some point, if the speed is too high, the normal force will go to zero, which will mean the tires will fly off the hill and the car will be airborne, and that's not safe. Okay, so by inspection we see, and here we're getting into the evaluation step here, so when v equals v max, when we just have the maximum safe speed, then n will equal 0. N equals 0 means your tires are just barely still on the road surface, but they're on the verge of flying off. So that tells us the maximum safe speed. So all we have to do in this equation is plug in n equals 0 and solve for v, and that will be the maximum speed. All right, so I'll go ahead and do that. Take this equation right here, and we write it as 0 equals mg, right, minus mv squared over h, or mv squared over h equals mg. I can divide both sides by g, or by m, sorry. The masses cancel out. So that means this problem is going to give the same answer no matter what the mass of the vehicle is. So this tells me that v max, I'll call it v max now because that's the condition for the normal force to go to 0. v max is equal to gh, or v max is equal to the square root of GH. And I don't have any numbers given, so that's basically as far as I can go with the answer. Units, I can definitely check the units to see if they work. What I'd have for the right-hand side, right, is I'd have the square root of meters per second squared times meters, because h is in meters, and that is meters squared per second squared. The square root of that is meters per second, and that's what I expect to have for an expression for a velocity. All right, so what we've learned in this problem is how to incorporate this acceleration formula when we have a problem involving circular motion. And we also learned something interesting. Whenever there's a problem that asks for what's the condition for an object to leave the road surface, or for something to fly off of a surface, that comes from the expression that the normal force goes to 0. And that's what we had to use here in order to take the last step towards solving the problem. I hope this is helpful as you tackle the homework problems, and we'll do more of these in class.